Okay, fantastic. Hello again, OSH 310 class. Just wanted to be able to throw in, this is our weekly review for week 3, mostly dealing with the topic of radiation. So I wanted to be able to take this time to go over some key points, some key words, as this week has a lot of reading and a lot of different things for you to study on your own. Hopefully this review can act as a way to focus your study so that you can best be able to know what to remember and what not to remember and what's important for this course. Be sure to still do the readings, as those can be able to expand a little bit more about what we're going to talk about, and it provides a little more, some of the more fun activities for the semester so that you can also better internalize the information. But with that being said, let's go ahead and get to the material. All right, so just as I said, this week is over radiation. Here's some specific topics that we're going to be going over in this weekly review. One, electromagnetic spectrum, ionizing radiation, non-ionizing radiation, and then health effects and regulations pertaining to radiation. So first, let's discuss the Let's discuss first the electromagnetic spectrum. Some of you, this may be the first time you've heard about it. You may have heard that song that was very popular in almost every chemistry or physics class in high school. But the electromagnetic spectrum discusses a wide variety of different types of both ionizing and non-ionizing radiation. It first starts, as this graph illustrates, and being able to describe radiation is a wave. And so whenever you're thinking about radiation, you need to be able to understand that it operates in a wave with ups and downs and frequencies and cycles. And that's able to better help understand how it's able to interact with different objects that it comes in contact with, including our own bodies as well. Some of these we interact with almost every single day, and you may not realize it, while some of them are a little less common. But ultimately, the electromagnetic spectrum just illustrates it, and being able to understand what are these waves, how long they are, and then also the energy that these different types of waves produce. So if we start off over here with the most left column, we have our very first one, which is radio waves. Radio waves, they're the longest wave. That means they take the longest amount of time for an entire cycle to be able to happen. A cycle is just at one point, and being able to, I don't know if you can see my mouse, but at one point at the very top of this, stinks it's a blue color, but at the very top of this hump, you could say, all the way to the next mimicking hump. That's one single cycle that this goes through. And that's ultimately what it's talking about with this wavelength on how long it is. And then energy. Now, wavelength and energy, they're inverse to each other, meaning when one is high, the other one is low. So the longer the wavelength is, the less energy that it has. One thing you could be able to use to think about that is the longer it takes for a cycle to be able to happen, for a wavelength to come to a complete cycle, that's a lot of energy it had to spend just to travel, that it has now less energy to be able to impact the object that it comes into contact with. Whereas we can move on to microwaves, then infrared, then visible, the visible spectrum, which is also known as visible light, ultraviolet, X-rays, and then gamma rays. As we go down here to X-rays and gamma rays, that's some of your ionizing radiation. And you can be able to see that the distance between these two cycles, so this top part and this top part, is a very small comparatively. Therefore, we go down here, it's about 0.5 nanometers. We can be able to see that the energy is way higher than it was back here with radio waves. So just to be able to illustrate that inverse relationship that wavelength and energy has, and that can be able to better determine, is this harmful, or how harmful is this substance? All right. we're going to be able to keep going on. And first starting at, oh no, the annotations, clear all drawings, fantastic. There we go. So first one we want to talk about is just radiation as a whole. Honestly, you need to be able to understand that radiation equals energy. That's all it is, really, whether it's concentrated energy inside of an atom or energy that expelling upon a certain substance. Radiation is energy that's either stored or being released. And there's a variety of different forms of energy with different characteristics, but typically it's split into two groups that we're going to go over: ionizing radiation and non-ionizing radiation. So ionizing radiation, that means that the radiation, radioactive source or the atoms themselves have enough energy to knock electrons away from the atom. That itself is defined as ionization. Whereas non-ionizing radiation, that means that the energy has enough for the atom to be able to vibrate and to move around, but not enough energy to punch an electron through. Always a little slow. Ionizing radiation is the very first one that we want to hit on, as it is typically the most serious one. And there's a little bit, quite a bit to it that we need to remember and keep in mind. So ionizing radiation typically occurs only with radioactive decay. So what that means is that this only has to do with unstable atoms, otherwise known as radionuclides. And what this is it's constantly, these radionuclides are releasing energy and thus getting smaller. This picture to the right is able to better illustrate this. So whenever you have a radioactive substance such as uranium-238, it is refer to it as the parent nucleus. So what happens is, as radioactive decay is happening, this nucleus, this parent nucleus, is literally decaying. It's shelling off and it's breaking down. You can be able to see from this that there's a line, it's going, and it busts off. That's an alpha particle. And so it's breaking apart. And so therefore, this parent nucleus no longer is uranium-238. Now it's actually the daughter nucleus of thorium-234. And if you wanted to be able to look more into it, it's 238 and then 234. There are 4 particles that ultimately came off with this. And so that it's really an active decay, and it's easy to wrap your head around that kind of effect. It really is, pieces and chunks of this are coming off of these atoms themselves. So there are 4 types of ionizing radiation that we need to keep in mind, that are especially the ones we're going to focus on. There are a few more, but these are the 4 ones we're going to focus on in this class. So there's alpha particles with right there the alpha symbol, beta particles with the beta symbol, X-rays, and gamma rays with the gamma symbol. And we're going to take some time to be able to go into these a little bit more in depth, but alpha particles should sound familiar because we just talked about that. For example, going from that parent nucleus down to the daughter nucleus, it sheds off an alpha particle. All right, so the very first one we're going to be talking about is, I was trying to see if it would give me a pointer, but I don't believe so. So hopefully you can be able to see my mouse. If not, I'll try to be as descriptive as possible. So the very first ionizing radiation particle that we're going to talk about is the alpha particle. So what this is actually the heaviest of the ionizing radiation types. It's made up of 2 protons and 2 neutrons. If you remember back to chemistry, the number of protons, neutrons, and electrons are critical to being able to define what the chemical is. The alpha particle is also otherwise known as, and illustrated here in the picture, a helium atom. It's the exact same. So whenever radioactive decay occurs and the element gives off an alpha particle, it's literally giving off a helium atom. And so that's definitely an important thing to be able to know, because it's very similar to how it operates. And so one of the things with alpha particles is that due to its weight as being the heaviest ionizing radiation type, it's actually the most damaging. Just due to its weight, it's able to interact and hit with, and really, it doesn't interact very well with different forms of cells, tissues, and also DNA. The nice thing about it is that whenever that atom gives it off, because it's so heavy, it's actually only able to travel a few centimeters. It doesn't really travel that far. And so that's where the only major concern that we have with alpha particles are if they're being swallowed or inhaled. So think of inhaling or drinking or eating a radioactive substance, typically a bad idea anyway, or if you're being cut. And that way it's able to make it into your body and potentially create more further damage to your cells and DNA while it's inside. The wonderful thing, though, as it is the heaviest and therefore the weakest in its potential energy, it can typically be just blocked by irregular skin or even by a sheet of paper. It really doesn't take much to stop an alpha particle, but it's very damaging if it's able to get inside of our bodies, as if we were to swallow or inhale it. So continuing on, the next one we're going to discuss is the beta particle. And so the beta particle, the easiest way to be able to demonstrate or to think of this is it's very similar to an electron. It's a particle that came from the atom and is now being emitted from the nucleus, and it has a negative charge to it. And so one of the biggest things with this, it's lighter than an alpha particle, so it's able to travel close to about several feet, maybe a few meters. And it's the negative charge factor that makes it unique, especially compared to the alpha particle. But it's important to be able to understand the alpha particle and the beta particle, they're physical particles. They have weight to them. So they are only able to travel a certain amount of certain distance before they lose that potential and kinetic energy. So the other thing is how it's different than an alpha particle is that it's able to penetrate more. So one of the biggest things is that it can penetrate through the skin and sometimes even through the entire body. It's listed there that it's not through the body, but it can. And it's also just how it can penetrate through the skin. But one of the biggest issues that it runs into is that it's typically a weaker or a slower particle in that way because it's more spaced out. Rather than being a concentrated helium atom like the alpha particle, this is one single particle that whenever it goes out, it has a bigger chance of hitting something and therefore being stopped and blocked. Whenever we run into this, we could be able to it could cause skin burns. It's also harmful if we inhale it because it's able to get past the skin. But for the most part, we could be able to protect ourselves with aluminum, wood, even sometimes just our clothes can be able to protect us from these beta particles if we were to potentially run into them. All right, next is X-rays. The biggest thing with X-rays is that this is actually the single largest man-made radiation source that we have. We're exposed to X-rays all of the time, and you may have already even thought about it. Last time you went to the dentist, you probably got an X-ray. Last time you went to the doctor for a broken bone, you got an X-ray. And so these are very, very common, but they are a form of ionizing radiation. And so the biggest thing with this is how X-rays are created. X-rays are created is whenever a foreign energy source comes in and it actually interacts with one of the inner shell electrons of an atom, and it causes that electron to go away. It causes it to completely go away from the atom. It bounces it off. And so what that does is that makes the atom extremely unstable. It doesn't like that. Again, if you remember from any chemistry classes that you've had, typically an atom then has these shells or these rings around it that hold electrons. You can be able to see from this right picture right here. So atom Za, and it has 2 electrons around it in that first ring. Same thing, it has 8 in the next one, and then maybe a couple in the outer one. So whenever this incident X-ray photon came in, or just an X-ray that was given, or just an energy wave came in, it interacted with this electron and caused it to pop out. And so what happened then is that a outside ring particle or outside ring electron then from this little arrow you can see moves down into an inner shell. And so from that, all of these shells require certain energy. Outside shell has a larger energy than the inner shell. So whenever that electron downgrades itself to then be in the inner shell, that energy has to go somewhere. So that atom just expels that energy away from itself. And this expelling of energy is otherwise known as an X-ray. And so that's how an X-ray is created. Energy comes in, knocks out an electron from an inner shell. An outer shell electron takes the inner shell place, and therefore the atom and the whole component has to give off some energy in order to stay equal. That given off energy is an X-ray. So an important thing as well, an X-ray is a ray. It's not a particle like the alpha or beta, so it's weightless. There's nothing really to it, and this one is ultimately emitted outside of the nucleus. Again, the red area is the nucleus of the atom. And so what happens is nothing interacted with the nucleus itself. All of this has to do outside of the nucleus, unlike the alpha particle and the beta particle. Those both had to do with the nucleus itself decaying. And so this is a lower energy and it will be less penetrative than the gamma rays. However, if you want to stop one of these, you're going to have at least a layer of lead or even a layer of concrete in order to be able to stop this. It's still very powerful, but it's not as strong as our next topic of gamma rays. So you may recognize this very top one. The most popularized ray, I think, for at least a bit science fiction is the Incredible Hulk, because the reason he became the Incredible Hulk was because of gamma rays and gamma radiation. And so gamma radiation occurs whenever there's a large molecular or molecule decay. It's not very common, but it does happen quite a bit. And so with that is an excited nucleus down here in the bottom right. An excited nucleus has a lot of pent up and stored up energy, and whenever it relaxes itself, it gives off an energy charge. And that energy charge that it gives off is otherwise known as a gamma photon. So gamma ray comes from an excited nucleus of an atom turning into a relaxed nucleus. So just like an X-ray, this is a weightless wave of energy. There is no weight to this. It's not a particle, but it is emitted from the inside of the nucleus like the alpha and beta. The other difference is that a gamma ray, it can travel thousands and thousands of meters. There's a lot of power to this, and as well as since it's weightless, it can just keep going. In order to be able to stop this, you're looking at maybe an inch, and think of an inch wall of lead, or even 1 foot of concrete, which is very different than an X-ray. For example, if you've ever gotten an X-ray, what they do is sometimes they have you wear like a vest, and the vest is not really that thick. It's really not. But compared to a gamma ray, there's a lot more protection that we need. So this is just able to illustrate again which one is the most penetrative. So an alpha particle, again, it can be stopped by paper or even just our skin. A beta particle, it could go through paper, even through our bodies as well, but could be stopped by aluminum foil. An X-ray and a gamma ray, those are typically both could be stopped by lead or concrete. But one of the biggest things that differentiates these two is the X-ray is not emitted from the nucleus. It has nothing to do with the nucleus of an atom, but the gamma ray does come from the nucleus of an atom. And then here are two other things. These are technically as well ionizing. However, we're not talking about those with neutron and neutrinos. If you ever want to look at something fascinating, look up neutrinos. Yeah, I'm not going to go into it. I don't want to confuse anybody, but that is a fascinating topic to be able to look at how they're created and what theoretically could stop them, because it's not much. All right, so the electromagnetic spectrum, let's look at it again. So we just covered the elements of ionizing radiation when it comes to the electromagnetic spectrum, which is the very top here, the X-rays and gamma rays. This is the area where the wavelength is the smallest, but the energy is the highest. It has the highest potential of doing damage to you, or interacting with your body in an adverse way. One of the most common things being disrupting cells or DNA, potentially leading to cancer. So now what we're going to do is we're going to be focusing on the left side of X-rays and looking at the non-ionizing radiation. So non-ionizing radiation, they're lower energy than ionizing radiation because they have longer waves. So again, longer waves means lower energy. Shorter waves means higher energy. So we interact with and use this radiation all of the time. All of the time. So let's go into some of those to be able to better understand how. So non-ionizing radiation, first one, which is the weakest, the longest wave radiation that we deal with, are radio waves. So some of the very common uses that we use this is AM, FM radio, television, and power lines as well. So one of the big things is kind of like AM and FM radio. There's a slight difference between those two. But if I remember right, I think AM is a little bit weaker than FM. That's why if you turn on like the radio to your car or even just like a stand radio on your nightstand or something like that, typically the one that we use all the time is FM. So it'll be like 98.6 FM. That's typically because the signal is a little bit more reliable. However, it's shorter. The wavelength is a little bit shorter. It can only travel a certain amount of distance. That's why across the country or across the world, different places can use the same numbers like 99.5 or 102.3. That's why, is because FM isn't as long of waves as AM, but it's a little bit more reliable because it does not have to travel such far distance. Whereas AM, what it is again, it's a wave that travels out, and there's a lot more potential frequencies than there are with FM. And so with AM, though, it's able to travel very, very far distances. For example, think of as far as a ham radio or things of this nature. They can be able to broadcast across entire countries or even in between countries. So I could turn on a ham radio and discuss a question dealing with environmental health in Brother Cardoni's class with someone in Australia just through the radio. And one of the biggest ways that it's able to do this, again, it doesn't have a lot of energy to it. So it's able to even be stopped by the clouds in the atmosphere that is around the Earth. And so you can be able to think of it, if this is Earth, I can broadcast here, it bounces and it bounces across the atmosphere onto the other side of the world. So it's a little bit interesting. We use radio waves all the time. Very similar, microwaves. So this is the second longest wavelength commonly found in microwaves, very aptly named, as well as cell phones and radar. So one of the interesting things is radar, it's a little more energy than radio waves. However, how a radar works is it pulses out energy, and just like when the lower right picture identifies, is that then it can be able to detect pulse energy coming back from hitting certain targets or certain objects that it was pointed towards. And so it does have enough energy to be able to go out, make it back, and we can be able to utilize that in a variety of different ways. Overexposure to this, it still can be able to affect us. If we're overexposed to this, research has been able to find it can be able to induce nausea, headaches, or even lack of sleep. So it's still, the exposure is not good for us, but it's still a lot better than some of those ionizing radiation sources. Continuing on is infrared waves. And so again, shorter wavelengths than microwaves. Infrared exposure to skin creates heat. And so what happens is if we're exposed to infrared, our skin naturally interprets that interaction as heat, and it can actually heat ourselves up. But another big thing is that the human eye cannot detect or see infrared waves. It can't. We can see other waves, as that we'll talk in the next time, but it can't perceive infrared or even any of the longer wavelengths. And this is commonly found, night vision goggles, TV remotes, even furnaces give off infrared waves. Next is visible light. And so energy waves that the human eye can detect. And so this can commonly be found in light bulbs or really any light that we are able to detect. Light in and of itself is just colors that the or colored radiation that is given off, because again, it's energy, and we can be able to perceive those colors in a to a certain degree. That's able to give us as far as color vision, and we can be able to interpret those energy waves into color. So with those, there's the lowest energy or the longest waves all the way to the highest energy and the shortest waves. And different color frequencies is another way to think about it. From the lowest energy, we have red, orange, yellow, green, blue, indigo, and the highest energy being violet. So it's good to know. However, it's not the most important to know, but visible light. So we can be able to see here, just again, it flipped from the one I showed you originally, so I apologize for that. But we can be able to see right in between infrared and ultraviolet or UV, we have the visible spectrum or visible light. And again, since infrared is a lower energy than ultraviolet, we can be able to see red, orange, yellow, green, blue, indigo violet. Yes, indigo violet. And so it's just another way of being able to understand how we interact with radiation on a daily basis all the time. It's not just nuclear power plants over in a far off distance. And then we have ultraviolet. So ultraviolet ultimately consists of three ultraviolet bands, types, sources that you can kind of think of. And I'm sure you might have heard of these before: UVC, UVB, and UVA. UVC, one of the biggest things is it can be able to cause possibly the most damage to us. However, it is almost completely absorbed by our Earth's atmosphere. So we really don't have to worry about that too much. There's also UVB. That's most commonly can be able to cause sunburns and eventually, in worst cases or repeated exposure, melanoma, type of skin cancer. Roughly about 95% of UVB rays from the sun are actually blocked out by the atmosphere as well. However, some does get through and it can cause quite a bit of damage. That's why one of the biggest advice, if you're going to be outside, wear some sunscreen. If you look on any sunscreen packet that you may have, you'll see that it has UVA and UVB protection. Same thing, your sunglasses. Next time you go look at sunglasses at a store or anything like that, be able to look at that. Some of the labels will say that this is specifically designed for UVA and UVB rays. And then UVA. So one of the leading, not the leading causes of wrinkles, but it can be able to cause skin damage and further exacerbate wrinkles on your face. So it's very important to take care of your skin, as well as can be able to cause some cancers, or at least be a contributing factor to cancer. Higher energy levels than visible light. Yes, so this is just a step below X-rays, and other places we can commonly find it. So the sun, but also welding, that's another perfect example of ultraviolet waves. One, we can be able to also describe it because we can't really see the color that's there. This is outside of visible light. So things that are too low of energy, our eyes can't detect it. However, things that are too high of energy, we also can't detect it. It all just looks the same. And so I believe that there are some animals that can be able to detect a much wider array of colors. And so it just means that they can be able to detect a wider array of radiation that's around them and be able to, their brains and eyes can be able to interpret those radiation sources in a different way. So then radiation health effects. So just like with any sort of health effect, whether you're in the medical field or really dealing with anything, there's acute and chronic. So acute, you can think short term and high dose. And so with that being said, two items come to mind whenever we're thinking of health effects of radiation, two stories, which is the an atomic blast or a nuclear reactor meltdown. So if you look in the bottom right there, this is actually a picture. If you know what it is, I mean, I would ask you to say it, but no one else is on this recording. But this is a picture of Chernobyl. in Ukraine. You maybe have heard about it. It happened, I believe, 20, maybe no, maybe like 30, 40 years ago now. But either way, it was a reactor meltdown, a nuclear reactor meltdown that we're still seeing the effects of today. So one of the big things is this reactor melted down, and then close to about, I think it was 100-kilometer radius around, a lot of the towns were deserted. That way, because of the acute or some low dose radiation that was also just being present even 20, 30 years from now. And one of the fascinating things is we're actually able to run studies and being able to understand and better understand the effects of low dose radiation because of this. It's a tragedy, and it's terrible that it happened. But there's some things we can be able to learn as a result of this happening, due to some of the animals that still live in those areas, particularly dogs. We've been able to find some of the effects of low dose radiation on how these dogs are, they're still having puppies and they're still carrying on a normal life, even though a few kilometers away, there's dogs that are not being exposed to radiation, living their lives. In addition to that, there is the upper picture. And if you know what this is, more kudos to you. I didn't know this until actually I had watched a movie on Netflix a little while ago, which is Demon Core. If you can find this movie and article about the Demon Core, absolutely would suggest it. It is fascinating. It's one of the, it's a little graphic in the sense that it is one of the most accurate movies in portraying what radiation sickness does to an individual. What Demon Core was in World War II, Los Alamos Labs in New Mexico was developing the atom bombs that were ultimately dropped on Japan, ending that side of World War II. That side meaning on that side of the world. And Demon Core was one of the follow-ups to Fat Man and Little Boy, the atomic bombs that were dropped in Japan. This was one of the follow-up nuclear warheads that was going to be potentially implemented if things didn't turn out the way that they did. It was a solid hunk of plutonium that was being experimented and researched upon. And what had happened is several scientists within a research lab in Los Alamos is that encasing that you can kind of see around it, there was a small little pinprick hole that breached into exposing the plutonium in the individuals that were around it. And the movie, it goes into a little bit more on what happened, but ultimately of the 7 scientists that were there, it was calculated that only the one that was closest to it wouldn't make it, regardless of any sort of medical intervention that kind of came through. A lot of the other people, they may be sick for a couple months or even a couple years, but this individual wouldn't make it at all. So he made it the last moments of life, being able to secure the Demon Core so that it wouldn't affect other people, and as well as continue on research, as he didn't last very long after that. So radiation isn't a joke. There's a lot of seriousness to it. Anyway, tangent. Now chronic. So this typically is referred to as long-term, low dose. So we can think of Chernobyl again, just like that bottom right picture. So when talking about the some of the animals that were around it, even 20 years from now, there's low dose radiation that they've been exposed to for the past 20 years, and that they're still being exposed to today. That, in also addition to such as sunburns, just because you get a sunburn once doesn't mean it's going to develop into skin cancer, but repeated exposure to the sun, UVA and UVB rays, it could then cause melanoma, one of the most common skin cancers that we have. So a lot of it just has to do with exposure duration and exposure intensity. So now ionizing versus non-ionizing. Ionizing has the energy to change molecules, that DNA or cells, and destroy them itself. And if the repair can't be, or if the damage cannot be repaired correctly, that's whenever cancer can be able to occur. A lot of it is just the malformation of cells replicating. Non-ionizing has some energy, but more functionality. We can be able to do a lot more with it, but in some degrees, it can still cause minor burns and slow acting damage over a long period of time. So exposure pathways. So radiation risk depends on a certain number of factors. So the energy that radiation being emitted, as well as the type of radiation. So whether it's alpha, beta, X-ray, gamma, UV, visible lights, microwaves, radio waves, whichever kind that it is, that plays a factor on how damaging it may be, in addition to its activity or how often it emits. And then if exposure is internal or external, just like with alpha and beta particles, so alpha particles are a lot more damaging if they're ingested rather than if they're on the outside because they can't penetrate through the skin. And then human metabolism as well. There are actually sources of radiation that we are ingesting and eating all the time, or things that have radioactive substances in it. But our body can take care of and metabolize a lot of those sources on its own. And then as well, where the radionuclide bioaccumulates in the body. So again, we're eating this all the time, but if we're looking at like thorium-234, thorium-234 may accumulate in the liver. So if we're ingesting a lot of, or being exposed to a lot of thorium-234, our body has a hard time of getting rid of it. And that's why it's in the liver to process it. But if the liver can't process it fast enough and we're accumulating too much of it, then that overexposure can be able to happen. So that's where it comes into effect, the TDS protection factors. And oh no, it looks like it's for some reason not there. Here, let me just add it in as we were talking. But so there are 3 different things to radiation management. That is time, distance, and shielding. Oh, I misspelled that. Okay. Shielding. Time, distance, shielding. Time meaning limiting how long you were exposed to something. So for example, if you wear a TLD badge, which we'll talk about, it is constantly looking at how long you've been exposed to a radiation source to tell you when do you need to stop and when is it going to be damaging after that. Then distance. And for example, the so it's how far are you away from the source. So one thing you can be able to think about with this is that the radiation source, just like a nuclear reactor, you can think about. If you're in your house and there's a nuclear reactor 1,000 miles away, that's definitely a lot more protective if something were to go wrong than if it was right down the street and something were to go wrong. So the farthest you can be from a major radiation source, the better. And then shielding, and I apologize, I'm going to have to write it under it, but shielding, you can be able to think of any walls or barricades to further kind of create a distance from it. So again, if you've ever had an X-ray, one thing that they typically do, like if you have an X-ray of your leg, they may give you a lead vest to be able to wear just so that it's not exposing your torso to any radiation. That would be potentially a type of barricade. Similar is that the doctor usually doesn't stay in the room. Usually they go into a separate room that might be lined with concrete or maybe even lined with lead. So those are walls or other barricades that are in there. But the TDS, time, distance, shielding, it's important to be able to understand that because that's some of the only controls that we have for radiation. Okay. Well, let me go. Okay. All right. So I got to clear that. Okay. So further going into, oh, well, I spelled it out here. Well, we already went over this. So again, limit time, increase distance, and then use shieldings like clothes, barricades, or walls. And then we have a TLD monitor. It's important to be able to understand this as well. This is a way to actively track what has been your exposure of radiation throughout an event, a day, or a period of time. For example, there are some radiation techs that what they do is they wear one of these to be able to monitor it. Once it hits a certain amount, they're done. So that's for a certain period of time, maybe for the month of, no, I can't be exposed to radiation anymore. Now they go work reception for the rest of the month because they can only be exposed to radiation for a certain duration of time. And so TLD stands for thermoluminescent dosimeter. So thermoluminescent dosimeter that tracks the exposure to radiation throughout an event or a time period. And so radiation, what are the limits? So just as I was speaking to a radiation tech in a hospital, they may wear one of these individuals, or the hospital deals with these type of events so frequently that they already have a standard in place to ultimately keep individuals underneath an annual limit. And so the U.S. Nuclear Regulatory Commission, or NRC, establishes annual limits whenever working around radioactive material or even just in general. And as long as you stay underneath these limits, their studies have been able to show that there really isn't any ill effect that comes from interacting with these substances. So the annual limit, if you're working with radioactive material, is 5,000 millirem. So mrem, millirem. And so in a kind of comparative is the annual limit for the general public. That they set that at about 100 millirem in addition to natural background sources. So what does that mean? Is they're saying that anything you do freely that might add to how much millirem of radiation you're exposed to, in addition to the stuff we're exposed to regardless of what we do. We actually are exposed all of the time to a variety of different things that are radioactive, whether it's things we eat, whether it's what our house is made out of, or even just what's in the ground or air naturally. And we'll talk about that in a second. But there's another one that is important to be able to understand. So the EPA, or the Environmental Protection Agency, they also set an action limit. An action limit is typically defined as when concern or controls should start to be implemented. And they've set that at about 4 picocuries. So it's a different unit of measure than millirem, but that's an important number to be able to understand. The EPA's action limit or action level for radiation starts at 4 picocuries. So regular daily exposure. So again, this is what I was talking about. Just common things that we're exposed to every single time that are actually radioactive and giving us doses of radiation throughout our day. And so some of the most common ones are the sun. So depending upon where you live and the elevation that you live, if you're at sea level, you're actually being exposed to radiation from the sun and cosmic radiation at about 26 millirem. And if you go up, I believe it's almost like every thousand feet that you go up, that means that you're being exposed to roughly about 4 millirem increase every 1,000 feet. In addition to that, housing material, that also makes a difference. If you have a house that's made out of stone, brick, or concrete, that's almost an additional 7 millirem. Well, food and water, so that's about 40 millirem. It's actually a banana, if I remember right, is calculated as I believe 0.01 millirem. So bananas specifically, because of potassium is naturally a radioactive material, even if it's very, very low dose. You could theoretically eat just a ton of bananas and be overexposed to radiation. There's no way you would eat that much. It's a very, very low amount, but in theory, I guess. So additional to that is just the general air that's around us, roughly about 200 millirem. And in addition to that, if you travel by jet, then it's estimated that you're exposed to 1 millirem, just further cosmic radiation, per 1,000 miles traveled. So if you travel from here to the other side of the world, you may be exposed to, I don't know the exact mileage that would be, but maybe another 7 or 8 millirem. And then also in the soil itself, that can further add to it. And one of the largest natural source of exposure to radiation. Again, X-rays are man-made sources, but natural source of radiation is radon. So if you live in a house that has a basement, it's very important to be able to test occasionally for radon, which ultimately comes from uranium changing to radium and then to radon. And so some of the biggest things, again, you can buy like household meters and household tests to be able to see what your radon exposure in those basements are, as it's found naturally within the rock and the general dirt that's underneath your house. And TVs, if you use a TV, about an extra 1 millirem. Same thing, medical X-rays. if you ever get them, could be about 40 millirem. It depends on what type of X-ray that you're getting. Luminous wrist watches, so anything with an LCD screen, yep, radiation, and many, many more. I would highly suggest that there's one link in the readings for this week, which is doses of our daily, I believe it's daily radiation. I have some things covering it. Yeah, doses in our daily lives. It sounds like a cheesy soap opera, but you can go through it and you can calculate this and see what is your actual exposure. I went through it and I found out that in a given year, I might be exposed to 500 millirem. Still under the regulatory limits, but it's something that's pretty cool or to keep in mind. So final thoughts. So we went to and we kind of ripped through this material, but again, heads up, it's a lot of material to look through, but hopefully this weekly review can give you some direction on what some of the important keywords and definitions and comparisons to be able to look at. Then definitely utilize the readings to be able to further branch out into what other information. But if you need a quick hit, this review can help. Same thing, this weekly review, just supposed to give you some direction towards important information, because again, I believe it's like 30 different articles that you're going to be reading. But ultimately, that's really it. So let me stop sharing. I thought I did. All right. Is it going to bring up? It did. Okay, fantastic. Well, I apologize about that. Some other things, be sure to check out the week 3 weekly assignments, or sorry, the week 3 weekly announcements, as I go into a few of the things that have been brought up to me by some other students, both some frustrations and some questions, particularly having to do with the how the quizzes are handled. That'll be very important as we dive in and move through the rest of the semester so that you can understand the expectations of the course. But thank you all. Hope you have a great rest of your week, and definitely feel free to reach out with any questions or any clarifications that you would like, or I guess have any questions of. All right, bye.